All right, so in the last bit, we talked about simple lenses and mirrors. In chapter 26, we'd like to put those together and talk about compound instruments and also how the eyeballs work. All right. So in the beginning of chapter 26, section 1, there are some super gross diagrams of eyeballs. If you're into that, go ahead and take a look. But I'm not going to go over that because they're gross.
And now we know why you didn't go into medicine. You're grossed out by eyeballs? Seriously?
Yes.
Okay.
Pictures of them, things, the thought that something might be touching an eyeball is especially distressing to me.
Okay.
Yeah. Early
So,
in my tutoring career, when I was still working as a tutor for the university, I did these group tutoring sessions, like supplemental instruction, and came into a room. Group of pre-med students were waiting for some physics tutoring, and they were watching a video of an open heart surgery.
that was not your jam?
I was so upset. I was so upset. And yes, Anthony, this is why I wear glasses and not contacts. 100%. I tried wearing contacts for a while, but I had to wear reading glasses anyway. So I was like, screw that. That is totally not worth it.
I'm sorry, what did I miss?
He's
Pe-
grossed out by eyeballs. I don't get it, but okay.
Yeah. I prefer that the insides of bodies just stay inside. I'll deal with the outsides of things.
That is fair.
Um, it takes
Guess
all
we weren't
kinds.
really meant to see the inside of it, right? That's yeah.
This
That's
this
fair.
whole this whole lesson, I've just been bouncing up and down in my seat because this applies directly to what I'm working to get into.
All right. So let's talk about eyeballs.
Yes, I saw
Eyeballs
this one coming.
eyeballs are basically oval-ish shaped. At the back is the retina where the image is projected, and at the front is the lens. So, and outside of the eye, there are objects that you try to see, and just like we were just doing, light comes in through your eye, gets refracted, and hits the retina at the back of your eye. Deep breaths. Okay. You can do this. The average size of an eyeball is about 2 centimeters from front to back. So if your eyeball is seeing something, that means that the image distance is equal to 2 centimeters. So 0.02 meters. Object distances, though, can vary quite a bit. I am told that people with normal eyes can focus on something as close as 25 centimeters and as far away as infinity. Right? You can focus on very distant objects. You can also focus on relatively close objects. The reason you can focus on a range of objects is because the muscles that control the contraction of your pupils can also change the curvature of the lens of your eye, thus changing the focal length of your eyeball when you focus on near versus far things. For far objects, we have our thin lens equation. Right? For things that are very far, the object distance is basically infinity, so 1 over the object distance is basically 0. So when you're focusing on really far objects, the focal length of your eye is about the image distance from your eye, which is 2 centimeters. For near objects, if you're trying to focus on a book that you're reading, 1 over the focal length equal to 1 over 0.25 plus 1 over 0.02. So this is about 54. And reciprocal of that is about 0.0185. So the focal length of your eye is about 0.0185. So 1.85 centimeters. Hey, Dolan, you made that a private message, but I feel like the whole class deserves to see it.
Want me to type it or just say it?
Yeah, I'm going to copy and paste. This is what Dolan just sent me in a private message. I have very mixed feelings about this joke.
Everybody's a critic.
Also, I think you saw this lesson calming. Yeah, but still, pretty good.
What can I say? I love a good dad joke.
Alright, so your eyeball can change its focal length based on what it's looking at. Awesome.
That's the way it works for all of you. And it still works okay for me, but not for much longer. That's why, right? I mean, that's what happens. As you get older, then it stops being able to change that. And that's why
Yeah.
I have to move things further away instead of closer in order to try to see them now.
That's right. So the most common reason for vision degradation is macular degeneration, which causes your eye to be unable to contract its focal length as much as it used to be able to. So, in fact, let's talk about that for a second. Do you need to memorize the focal lengths of your eyeball for this chapter? I mean, you don't, but why wouldn't you? So I'm super blind. To actually read a book, I have to hold it like 5 centimeters from my face rather than 25 centimeters from my face. Um, okay. So this is because I'm nearsighted. If you were farsighted, this would be you'd have the opposite problem, right? But for nearsighted people like me, I actually have trouble um, expanding the focal length of my eyeball. So focal length of my eyeball at if I can read it at 5 centimeters away from my face, focal length's about 0.0143. Let's actually take that, give ourselves some space. And let's think about a compound eyeball and lens system. Eyeball, lens. Eyeball is about 2 centimeters long. Distance from lens to eyeball, about 1.5 centimeters. And I want to be able to read a book at a normal distance. So what focal length of lens do I need in order to correct my near vision? When you have a multi-lens system, the idea is to take the image for the first lens and to use it as the object for your second lens. So in other words, let's start backwards from the eye. If I wanted to be able to resolve an image normally, right? So given this focal length for my eyeball, what object distance would I need in order to have an image distance of 2 centimeters? So 1 over f equals 1 over di plus 1 over do. Focal length is this thing up here, 0.0143. Image distance, right? 2 centimeters. Object distance. Oh my goodness, you people. You're still punning in the chat. I don't even know how to respond to that. So if we take a look at the calculation that got us here in the first place, we'll realize that the object distance needed in order to resolve using my crappy eyeballs is about 5 centimeters. That means that we need a 5 centimeter distance between eyeball and the image due to the lens. Right, so the actual image distance has got to be 5 minus 1.5, so that's 3.5. But because it's actually on the same side of my glasses as the objects, that's going to be a negative image distance. So now we use the lens equation again. 1 over f, this time for my glasses, not for my eyeball. It's equal to 1 over di plus 1 over do. We just solved from the first bit that the image distance we need is minus 3.5 centimeters, 0.035. The object distance I want to be able to read my book at is 40 centimeters. I'm going to pull out my calculator momentarily. All right. So this means that my glasses would have to have a focal length of negative 3.8 centimeters. Right, and actually, I just kind of spitballed some numbers here. This would mean that my prescription would be negative 26 diopters. Actually, I can read a little bit further away than 5 centimeters, but not too much further. Okay. Questions or comments on this lens plus eyeball system? Nothing? Okay. Cool. So that this couple of problems here, this is basically 26.1 and 26.2. 26.3 is mainly an interesting bit, but there's no actual testable questions within it. So you should definitely read it because it's all about how our eyes form color images, but I'm not going to be testing on it. So there's eyeglasses, let's talk about microscopes. Microscopes are for enlarging images that are really small. And typically, the object distance is also really small. Like we put the end of our microscope right up on the thing we're trying to look at. So the microscopes people are used to were probably vertically oriented. So there's our objective tray where we put this is our specimen tray. And then really close to that is the end of our microscope. And it's this tube. And then at the top of the tube, you put your eyeballs there to take a look at whatever's going on. There's two lenses in a microscope. The one at the bottom near the specimen is called the objective. And the one at the top next to your eyeball is called the eyepiece. In a typical microscope, I mean, I've got a relatively low power microscope that my son plays with, and the tube here is about 25 centimeters. And it produces about a 40 times magnification. Microscopes are cheap these days. You can get a 40x microscope for like $20 on Amazon. Everybody should have one to play with. All right. So when we have multiple lenses and we're trying to get a magnification, the total magnification is equal to the product of the individual magnifications. Right? So if the objective lens has a magnification of say 20 and the eyepiece has a magnification of 2, that gives us our overall magnification of 40. Let us say that for here the focal length of the objective lens is 6 millimeters. The focal length of the eyepiece is like 50 millimeters. My question is, how far away should my specimen tray be from my objective lens? Like, right? Like, how big should this space in here be? So I'm going to redraw this diagram a little bit, but I'm going to lay it on its side. Right, so we have specimen, then we have objective, then we have eyepiece, and lastly, I lost my train of thought for a second. Yeah. No, that's it. Oh, yeah. Then we have your actual eyeballs. So, of these distances, there was, this is the distance that we want to find here. This distance between the lenses is 25 centimeters, and the distance here is usually like 2 centimeters. Right? The overall magnification of this thing is 40, and like I said, the eyepiece has a 2 times magnification. The objective has a 20 times magnification. So, if with this information, all right, serious time in chat for a moment. If you need to make an image 2 centimeters behind the eyepiece lens, and it has a 2 times magnification, what does your object distance need to be? Actually, hold on. Let's do this a little bit differently. There we go. So we write down the thin lens equation for both lenses separately. So for the objective lens, we have 1 over its focal length equals 1 over x, which is the object distance, plus 1 over di, we'll say O for the objective. We also have a similar equation for the eyepiece, 1 over the focal length of the eyepiece is equal to 1 over the object distance of the eyepiece plus 1 over the image distance of the eyepiece. Okay. Because the two lenses are 25 centimeters apart, we also we have a relationship between the image distance of the objective lens and the object distance of the second lens, right? So the object distance for the eyepiece plus the image distance for the objective lens is equal to the length of this tube. Okay, so quick check. Of the 3 equations we've just written down, how many unknowns are there in these 3 equations? I'm sorry?
3. 3.
So we don't know x, right? We don't know the image distance for either of the image distances, and we don't know the object distance for the eyepiece. So by my count, that's 4. We actually don't even need that. So for 4 total unknowns, we need 4 total equations. Right? We want an overall magnification of 40. So 40 is equal to the image distance for the objective divided by the object distance for the objective times the image distance for the eyepiece divided by the object distance for the eyepiece. So there's 4 equations, 4 unknowns. We can totally solve this, right?
Yes, definitely. I would have a lot of fun doing that, actually.
Okay.
But it would take a minute.
Yeah, it would take a minute. It's not technically demanding. It's just a little bit tedious. Right? If we have 4 equations and 4 unknowns, we can solve and substitute, solve and substitute, solve and substitute, get an answer. So yeah, not technically demanding, right? You did a bunch of this in General Physics 1, so I know that you all know how to do solve and substitute. So yeah, so we're not gonna, I guess we're not gonna finish this problem off, except to say that, of course you could, and that would make a good quiz question next week, wouldn't it?
Okay, I got the screenshot before you went away.
So that's microscopes. We have 2 lenses separated by a distance. We are trying to get a large magnification, and the original object is real close to the first lens. So then what's the difference between a microscope and a telescope?
Distance between the object you're looking at?
Yeah. They work essentially the same way, except that your original object distance is so far that we do the 1 over object distance is basically 0 thing.
Imagine size of the object would have a lot to play in that equation.
Yeah. So the kinds of things we normally look at with telescopes are far away but large, right? So when we're looking at a microscope, normally what we look at is we get quoted the total magnification. So you buy a 40x microscope, right? For a telescope, what you're usually looking at is the angular magnification. That is, like what fraction of the sky does the, so if we're looking at a star, right? So if we're looking at, actually let's say we're looking at the moon, right? And here we are on Earth. So the apparent angle of the moon is, right, how much of the whole sky does the moon take up? Right? There are pi radians of sky visible to us. At least if there weren't any mountains, there would be pi radians of sky visible to us. So what is the apparent angular size of the moon? And maybe this is actually something that's worth pulling out, actually. Since telescopes work relatively similar to microscopes, I'll let you get grab the differences from the book, but let's do a different kind of calculation here. So you are viewing the moon, right? How big of an angle does the moon take up? And we get to use some interesting trig here. So the diameter of the moon is something that we can look up, right? Or more likely, you'll look up the radius of the moon. What is the radius of the moon? Anybody got a quick Google hand? Radius of the moon.
1,079.6 miles.
Dude, what class are you in?
Just looked it up and that's what it said.
In miles? It's about 1.7 million meters.
See?
And so that's this distance here. What is the distance from the Earth to the moon? That is the distance from the moon to where we are looking at it. Nobody? It's about 385 million meters. Okay. In radians, let me clean up this picture a little bit. There's a couple ways we can think about this actually. Oh. If we divide this view in half, we've got basically a right triangle there, right? So we've got something that's a right triangle. The angle is theta over 2. It's a right triangle. This is the radius of the moon here. This is the Earth-Moon distance here. So we could say that the tangent of theta over 2 is equal to r over d. You may notice r is a lot smaller than d. It's less than 1%. So we can use what we call the small angle approximation, which is that for small values, for small angles, the tangent of an angle is approximately the angle in radians. So tangent of theta over 2, if theta over 2 is small, is approximately just theta over 2. So the angle that the moon subtends, that's a technical term, so subtends is the angle that it appears to take up in the sky. It's about 2 times r over d. 2 times 1.7 is about 3.4. 385 is about 340. So 2 times r over d is very loosely about 0.01. So 0.01 radians is the apparent size of the moon. and there is a nice result. It's in your book, so I'm not going to derive it here, but the angular magnification of a telescope. We can define that as the angle that the image takes up over the angle that the object takes up. It's also equal to the ratio of focal lengths between the eyepiece and objective. Objective over eyepiece is what I meant to say. So if you've got the same lenses that you used in the microscope, right? So in the last problem, we had a focal length of 0.006 and an eyepiece of 0.05. You notice that those lenses don't actually work for a telescope because we'd get a magnification smaller than 1, right? So we need an objective lens with a larger focal length. So maybe let's reverse those. So basically, think of this as taking the microscope that we had in the last problem and looking through it in reverse. So we get an angular magnification of about -8. So if we take those same lenses, we look through them in one direction, use them as a microscope, we get a 40 times absolute magnification. If we look through them in reverse and use them as a telescope, we get an angular magnification of about 8 1/3 times. Right? And that's basically the idea between microscopes and telescopes. Same materials, using them backwards. All right. Questions or comments? That is all of chapter 26, by the way. Is everybody just ready for the weekend to start?